This is first video on statics of planar forces. Here we are going to deal with concurrent forces, and we are going to look at how to find the resultant of concurrent forces which are lying in one plane. Now before we do that, it's worth looking at the overall plan of study of statics of planar forces. There are two parts. One, concurrent forces, and other non-concurrent forces. That is, in one plane you can have either concurrent forces, that is those who pass through one point, and second, non-concurrent is those who do not pass through one point but still lie in the same plane. Now in concurrent forces there are two types of problems. One is finding resultant, and second is solving equilibrium problems. Equilibrium problems have many applications. Two of them are here. Cylinder and sphere type problem, or just when concurrent force system is given, we are required to find two unknowns instead of resultant. In non-concurrent forces also there are two types of forces, two types of problems. One is finding resultant and another is solving equilibrium problems. And in equilibrium problems we can have many applications, that is beams, trusses, frames. We are going to deal with all of them, but this video is devoted to learning how to find resultant of concurrent forces which are in one plane. We need some background and understanding about resolution of forces. Let's say I have this force F1 equal to 40 Newton inclined at 30 degree with x-axis. I want to resolve this force in x, y and z direction. Then 40 cos 30 is component of this force in x direction. 40 sin 30 is component of force in y direction. And 40 cos 90 is component of this force in z direction. So in vector form this force can be written as 40 cos 30i plus 40 sin 30j plus 40 cos 90k, meaning 40 cos 30 is x component of this force, 40 sin 30 is y component of this force, and 40 cos 90 is z component of this force. Now cos 90 is 0, and if we are going to deal with planar forces, for any force in this plane, angle with z axis is always going to be 90, and therefore cos 90, the z component of any planar force which is in xy plane will always be 0, and therefore this force in a vector form is popularly written as 40 cos 30i plus 40 sin 30j. Now see, this technique of resolution we need to master. Either we talk about expressing force as a vector, or we say that the force is resolved in x and y direction, and the components are as shown here, 40 cos 30 and 40 sin 30. Let's say I have force in first quadrant, but now towards origin of magnitude 40 and inclined at 25 degree with x-axis. Now if I try to resolve this force, it will look like this: minus 40 cos 25i minus 40 sin 25j. Understand the method of resolution which I am proposing. We will always take angle with x-axis. Okay, the smaller angle, in the sense with x-axis, if 180 minus 25 you do, that is also inclination x-axis, but we will take a smaller angle with x-axis, that is 25 degree. If we do that, then x component is always cos and y component is always sine. When it comes to positive and negative sign, we have to see in which direction the resolved component is. If it is in negative x direction or negative y direction, the signs will be negative. Therefore, as you can see, x component of this 40 force is minus 40 cos 25, and y component of this force of 40 Newton is minus 40 sin 25. Now, if your force in the second quadrant of magnitude 50 and inclined at 40 degree, then the components will look like minus cos 40i plus sin 40j, and magnitude you are multiplying. So the vector will read as minus 50 cos 40i plus 50 sin 40j. Let's say your force in fourth quadrant of magnitude 80 and angle 60 degree with y-axis. This force in the vector form will look like 80 cos 30i minus 80 sin 30j. See, I have always taken angle with the x-axis so that I can set up a system that I'll only deal with one angle 30, which is with x-axis, and x component will cos and y component will be sin. Finally, in third quadrant, if I have force 70 inclined at 15 degree with y-axis, I will write its vector form as minus 70 cos 75i minus 70 sin 75j. Now, this technique has to be mastered, because the resultant what we are trying to force is after all an equivalent force, and it is nothing but vector addition of all these forces. And what you mean by addition, vector addition of all these forces, is you club all the x components, add them up, club all the y components, add them up, and what you get finally is x and y component of the resultant. This problem will make all these things more clear. Let's say a problem which reads like this. Determine the resultant of the 6 forces as shown in figure. So here are 6 concurrent forces, and what I'm going to do is sum up their x components. They are 20 cos 25 minus 30 cos 45 minus 40 minus 50 cos 60 plus 70 cos 30. I sum up y components. 20 sin 25, 30 sin 45, minus 50 sin 60, minus 60, and minus 70 sin 30. Then what I have, this sigma fx and sigma fy, is actually x and y component of the resultant or the equivalent force, and therefore to find this magnitude, all you have to do is square them, add them, and take under root. We get 108.89. And if you want angle of inclination, all you do is do sigma fy by sigma fx. That will be tan theta. Take tan inverse and you will get the angle, which in this case comes 86.07 degree. But merely leaving answer like this is not enough. We need to show it on the figure. And if I try to draw it on the figure, it will look like this. 108.89 at 86.07 degree in the third quadrant. Why is it in third quadrant? Because sigma fx, sigma fy both are negative, and the angle sigma fy upon sigma fx, the tan theta, what theta we get is always with x-axis. So physically what it means is, to this point either you apply the 6 forces or apply this single force which is shown in blue color and which we are calling resultant, and the point will feel the same way. In statics, what you mean by feel? It will move in the same direction and accelerate the same amount as if 6 forces were applied to it. The single force, the resultant, will do that same job. That's what we mean by the resultant. Let's look at second problem. Which says determine the resultant of 3 forces acting on hook as shown in figure. Now, as far as we are concerned, we are bothered whether forces are concurrent or not, and whether they are in one plane or not. Whether they are acting on a hook or something else is none of our interest for purpose of solving the problem. So here are 3 forces All I do is same method I follow. I resolve them in x direction. They come to 80 cos 25, 70 cos 50 and 50 cos 45. Add them up. Then do the same thing for y. Sigma fy 80 sin 25, 80 sin 50 and minus 50 sin 45. Find sigma fx, sigma fy, square them, add them, take under root, find the angle, and like before, show it on the figure. Answer is 161.48 Newton at 18.81 degree with x-axis in the first quadrant, and the reason for it being in first quadrant is sigma fx and sigma fy both are positive. Look at one more problem. Here, 1, 2, 3, 4, 5 forces. The problem reads like this. A gusset plate of roof truss is subjected to forces as shown in figure. Determine the magnitude of the resultant force and its orientation measured counterclockwise from positive x-axis. As I said earlier, let it be part of any machinery, truss, hook or whatever. Our concern is forces are concurrent, and if they are in one plane, we follow our standard method of summing up all the x components. That is 180 cos 0 minus 180 cos 45 plus 160 cos 45 minus 200 cos 0. Again, you add up y components. That is sigma fy 240 sin 90 minus 160 sin 45 minus 180 sin 45. You get sigma fy. You already have sigma fx. You square, add, take under root. You get magnitude of the resultant. Sigma fy by sigma fx. You get direction of the resultant. Now here, mind you, if you do sigma fy by sigma fx and do tan inverse, actually angle you will get is 0.17. But what they have asked is measured angle. They want angle measured counterclockwise from positive axis, x-axis. So we added 180 degree to it, and here is how the resultant looks. Thank you.